All right, we're going to jump back into section 13.5, hopefully finish it on up today. I believe we're on example 3B. Is that right? Awesome. Okay, so we are in the process of manipulating values into different units. And we're doing this in this section in regard to volume, which actually triples what's happening because you're multiplying it by itself 3 times. So on part B, we have 365 millimeters cubed, and we are attempting to change it into decimeters cubed. So what we want to think about in terms of our relationship, and you can write like the King Henry died by drinking chocolate milk if that helps you as a reference point. On this one, we're trying to get from millimeters, which is over here on the far right, over here to decimeters, which would involve moving it 2 times, right? A decimal point 2 times. While we can move the decimal point 2 times, and then because it's cubed, we would do that 3 times. So 2 times 3 would be 6. We'd move the decimal 6 times. You can also set it up with a fence if that helps you to keep those dimensions in mind. In particular, thinking about how millimeters are related to decimeters. And the relationship is that 1 decimeter is 100 millimeters. But I need to do this to be cubed, like so. What that means is that 100 needs to be cubed. So instead of just a 1 with 2 zeros, I'll have 4 zeros and then 6 zeros since I've done it times itself 3 times. So I really end up with 365 divided by, is that a million? I think it is. Now that's equivalent, if you think about it, to moving the decimal 6 times because there's 6 zeros underneath there. So again, that comes from the fact that the decimeters, I can't reach up there. The decimeters and the millimeters are 2 apart, right? And so you move it 2 times because they're 2 apart, and then you move it 2 times because you're squaring, and then you move it 2 times because you're cubing. So you move the decimal point 6 times. So my decimal point ends up becoming, or my value ends up becoming, written down here, 0.000365 if I move the decimal 6 times. That goes in that decimeter spot. I'm kind of out of space, so I'll just put the decimeter cubed over here after it. But it should go right here. So it's up to you whether you do fences with metrics, but they're very helpful when we're doing them for things that are not metric. Let's take a look at C. C takes inches cubed into yards cubed. So we have 874 cubic inches, like so. And we may or may not know, depending on what you've done, a relationship between inches and yards directly. Maybe you do. If you do, that's great. If you don't, I'd like to show you what happens just in case that's the case. We do have an inches to feet relationship that we're all aware of. That is that 12 inches is in 1 foot. I do need to cube these things. So that's really 12 cubed underneath there. I don't know what 12 cubed is, but we're about to find out. Apparently it's 1728. And then we would do it one more time to turn my feet into yards. So what's the relationship between feet and yards? What's that, Emily? Just think about the yards and the feet right now. What's the relationship?
27.
Okay, we have one written on the other page. Is that what you're looking at? Okay. So also keep in mind if you don't have that one, because you guys are only going to have a limited amount of things you're going to be able to write down on a note card, you should know that 1 yard is the same as 3 feet. Y'all know that, right? Okay, good. And if you cube it, that's where that 27 is coming from. So this is a 27 down here. Does that make sense to everybody? Where that 27 came from if you didn't have that fact written down or decided it wasn't worth writing. So my feet cubed cancel, my inches cubed cancel, and I'm left taking the 874 and dividing it by 1728 and then dividing it by 27. And if we do that, we actually get 0.019 yards cubed. Or if you were to do two decimals, it'd just be 0.02 yards cubed. That would be fine. Most of the time we've done two decimal places. I'm not sure why I wrote down 3 on that one. Okay, any questions on that one? Okay, let's take a look at a couple of them now that are a little different because they involve some liquid measurements. This says 37 gallons into cubic feet. So I've got to get out of gallons and into cubic feet. Okay, so this is probably my table that's going to be most helpful because I do have gallons on this table. I don't have gallons just sort of like everywhere though. It's right here. It doesn't turn it into cubic feet, but it does turn it into cubic inches. And I do know a relationship between inches and feet, so that's probably the one I want to use. 1 gallon is 231 cubic inches. So 1 gallon is 231 cubic inches. And because it's already given in cubic inches, I don't need to cube the 231. That's actually part of the conversion already. But like we said before, we really don't want it in cubic inches, we want it into cubic feet. So if I'm taking my inches then into feet, and I want to use just this basic conversion I know, then it's 12 inches into 1 foot, and I would cube them. I cubed the 12 just a moment ago. It was the 1728. So my inches cubed cancel and my gallons cancel. And I'll end up with multiply across the top 37 times 231. It's like 8547. And then divide by 1728. And to 2 decimal points, I have 4.95. What are my units? Yeah, feet squared or square feet. I'm sorry, cubed. Cubic feet. There we go. Okay, the last one that's on here is cups into cubic inches. So we see a relationship between cups and pints and ounces at the bottom. Doesn't really seem to be super helpful. I do get something in inches cubed near sort of the middle right there, one I highlighted with the gallons right there. So it might be more helpful to think of changing my cups into gallons and then my gallons into inches cubed. Does that make sense? So I can use that same green one that I did before. So we have a relationship, here's 97 cups, between cups and gallons. And every time I do this, I think of like a gallon of milk. That's my reference point for a gallon. We buy gallons of milk in our house. So do you know how many cups are in 1 gallon? It is 16, and you've got lots of visuals that I've shown you for that as well. That would get my cups into gallons, and then I can use that same relationship that I did in the previous problem to do my gallons into cubic inches. So my 1 gallon is 231 inches cubed, or cubic inches. So my gallons cancel, my cups cancel. I will end up having 97 times the 231 straight across, and then divide by 16. That ends me up with 1400.44 cubic inches. to 2 decimals anyway. Okay, so it's more of the same. It's just a little more tedious because there's cubic things going on that we sometimes actually physically have to cube the values unless we want to write a lot of the values down in our notes. So let's actually look at some volume formulas. Volume is actually quite a bit easier to do than surface area. So you guys did 13.4 about surface area before you did volume. And volume tends to be easier to work with. First, we're going to do volume of prisms. The volume of a right rectangular prism. Does anybody know this one? Yep, length times width times height. And that's one that we tend to remember. So that's a right rectangular prism, right? The ones that go straight up and down. We also have ones that slant, right? Imagine Leaning Tower of Pisa, but in a prism form. So a slanted type of a shape. It actually gives you sort of this note right here that B is the area of the prism's base and H is the prism's height. So if B is the area of the base and H is the prism's height, and it means that perpendicular height, right? Not the slant height, but perpendicular height, then your volume here is actually to take the area of the base, which is capital B, times the height. And if you look at that, that's really just the same as the first formula when it's actually a right shape, length times width. It's whatever the area of the base is.
So that would be the same?
It's just a specialized case. The right rectangular prism is a special case for a right or oblique any kind of prism. So like notice that the pictures over here show you a couple other shapes. In particular, you have one that has maybe a parallelogram on bottom. Well, I don't necessarily find the area of the parallelogram the same way. I have a triangle on bottom. I don't find the area of the triangle quite the same way, but whatever those areas are, just like with my right rectangular prism, that's what ends up getting multiplied by my height. All right, we're going to take a look at several more, and then we're going to do all of the examples together. Volume for a cylinder, much easier to work with than the surface area for the cylinder. The volume for the cylinder, where r is the radius of the circle's base and h is the cylinder's height. The volume is pi r squared, that's the area of the base, times the height, just like the formula before. I just happen to know that the area of the base is pi r squared because it's a circle. That's a right circular cylinder. If I happen to have a cylinder that maybe has an oval at the bottom, right, or some other sort of a different shape that's curved, right, but it's not a circle, then I would do much the same way I do before. I would take the base, whatever that area of the base is, times the height. So a right circular cylinder is simply a very specific type of cylinder where I know the area of the base formula. Okay, we've got pyramids and cones left. On a pyramid, we have a shape that's kind of like a prism, right? It has these sides that are flat instead of curved with our cylinder kind of shape. We have these flat sort of sides, and its volume ends up being 1/3 times the area of the base times the height. And again, that keeps it the most vague for us, so no matter what that base is, if it's a square or if it's a pentagon or if it's a decagon, we could find the area of that base and multiply it by the height of the object. And then the last one on this slide here, the circular cone, I have one more after that. A right circular cone is very similar in the way that it conducts itself. The volume is actually another 1/3 because of this triangle sort of feature going on because it has an apex and so forth. And it's pi r squared h. So there's that area of that circle, right? That's my area, my base. It's pi r squared. Just like the base right here is listed just as a b. The area of the base here is unknown. The area of the base on the bottom is a circle, so it's pi r squared times my height h. And the last one is our volume of a sphere. So the volume of a sphere is actually 4/3 pi r cubed. That one's the exception to being not as nice of a formula as the surface area formula. Surface area was a little nicer, had the whole number 4 and r squared instead. All of these other formulas are a fair bit nicer because they don't have any addition of different pieces and different shapes of pieces. I end up with one single multiplication to work with. All right, so we talked about this particular cone last time. We did the surface area of this cone. That was like the last example in 13.4. And here we're going to find the volume of the cone. Now you have to recognize, though, that we have two different shapes here. We have the hemisphere on top, right? And then we have the cone on bottom. So we have to find two pieces of volumes. But the volume formulas themselves are much nicer. The fact that it's a hemisphere, it's half of a sphere, means it's half of the sphere formula. So the sphere formula was the one I just did on the previous slide, was 4/3 pi r cubed. And I've got half of it because I have a hemisphere. Now, this was a little tricky when we did the surface area because we had to eliminate the pieces that were sort of stuck in the inside, right? So for the cone, we couldn't consider the top of the cone because it was embedded inside of it instead of being on the surface. Volume doesn't have that sort of caveat. There's nothing about it that's counting surfaces. It's just the volume of the shape itself, and it doesn't change whether, if you cover up one side with a hemisphere or not. So my volume area for my cone that I did just a moment ago was 1/3 pi r squared h. So I'm just applying the two pieces of the formula that I need, the sphere and the cone. And I'd like for you to take a look with me and tell me what in the world actually is my r and what is my h. R is 4 and h is 8. So I'm going to take this 1/2 and this 4/3. I'm going to multiply them and get 2/3. Right, so this 2 and this 4 would reduce to 2/3. And then I have pi. My r, you told me, was 4 squared plus 1/3 pi. R is 4 squared times h, which is 8. We'll simplify some of this down first, and then we'll turn it into decimals. But if you want to turn it into decimals quicker, that's okay. Yes, Emma?
Why did the 4 go to a square?
Because I typoed. Let me fix it. It shouldn't have. Thank you. It should still be cubed. Okay, excellent. So do you guys know what 4 cubed is? It is 64, yep. And then over here I have 1/3. 4 squared is 16, and then 16 times 8 is 128. So 64 times 2 is actually also 128. So 128 pi over 3, oddly enough, plus another 128 pi over 3. That will not always happen. That was just sort of a lucky chance kind of thing here that worked out. Emily, you look confused.
Did you just put an imaginary 1 under the 64 and then multiply those fractions?
Yep, I just multiplied the 64 times the 2, as though there was a 1 underneath it. You can think of it that way, sure. 128 plus 128, what is that? It is. So 256 pi over 8. 3, not 8. I don't know where I'm getting an 8. 3. That would be the exact value of the volume. For most of the problems that you do, it asks you to turn it into decimals. So let's try that for now as well as a practice sort of thing. So if I take 256 and I take my pi times my pi divided by 3, this is approximately 268.08. I still need units, but is that okay in terms of numerical value for everybody? What are my units? Centimeters cubed. Good job. Remember that it's cubed because we're working with volume. Okay, we have a couple more. Volume of a right triangular prism. Now, we had a formula for a right rectangular prism, but we had this sort of generic volume for any other prism that said that I take the area of the base times the height. All right, so this is the area of the base. All right, so my base is a triangle. You actually know the formula for the area of a triangle, right? What is the formula for the area of a triangle? I think I'm going to do this on the side. Yeah, so it's the height of the triangle specifically, not of the whole object. But yeah, so I need this particular shape. This is what I'm finding here. So what is the base? 6. What is the height?
6.
Happens to be another 6. And if you multiply 1/2 times 6 times 6, what will you get? Close. We're multiplying 1/2 times 6 times 6. 18 is it, yeah. 18. So my area of my base up here is 18. Now what's the height of the actual prism? That's the height of the pyramid. Of the triangle. What's the height of the prism? 12, yeah. The height of the prism itself, or you can think of it as length since it sort of looks like it's on its side, is the 12. That's the dimension I haven't dealt with. So this is 12 times 18, which is 216. And what are my units? Centimeters cubed, yes. All right. One more example in this section. Do a straw. Do any of you like straws? I see some of you have straws in class even. We're straw people in my house, except for my husband. He hates straws. Don't know. So we have a standard straight drinking straw. It's 25 centimeters long and 4 millimeters in diameter. How much liquid can be held in the straw at one time? Okay, so we have this shape. And I'm definitely not drawing it to scale, but I want to draw a cylinder. It's 25 centimeters long, but it is 4 millimeters in, did it say diameter? Yeah, in diameter. So it's 4 millimeters across here. I need yellow to work better. So do you see an issue right at the outset? What's the issue you see, Julie? Say again. We do need volume. That's true. There's something else, though, with the numbers they give us.
They give us the diameter instead of the radius.
They did give us the diameter instead of the radius. That's important to notice. Avery.
They're different units.
Yeah, that's the one I was going for the first part. Although the other issues will all come into play in a moment. My units cannot be different in this problem work out well. They need to match. So I need to decide to either use millimeters or centimeters. And it doesn't really matter which one you pick, but we need to pick one. So which one do you guys want to use? Okay, I think millimeters is what people are saying. Okay, so I already have my 4 millimeters on top. What would I have to do to get my 25 centimeters into millimeters? Yeah, I would need to move the decimal to the right once. So right now it looks like this, and I need to move it. So this is going to be 250 millimeters. Again, if you change it into millimeters, or into centimeters instead of millimeters, that's totally fine. I'll just use your answer in centimeter form when you're done instead of millimeter form when you're done. Doesn't matter. Okay, now there is a formula for the area of this, the volume of this object. What's the formula for the volume of a cylinder? Yep, pi r squared times the height. Now let's go back to an issue that you mentioned, Emily. So we got the volume formula, kind of what Julie was pointing out, relationship between the height and the volume. And then you had mentioned, Emily, that we needed to have the radius and not the diameter. So what's the radius of this object? It's 2. So we want to be careful that we use the right value. So we're going to have my pi, my radius is 2, and then it's squared, and my height is 250. Okay, is everybody good with all the pieces where they sort of landed? Okay, so if I take 2 squared, I get 4, and 4 times 250 is actually 1,000. So this is 1,000 pi. And if I multiply that out with the pi, I would actually get 3141.59. I switched into millimeters, so this is millimeters cubed. If we had done this problem in centimeters instead, my answer would have the same value, like all the digits would look the same, the decimal would just be in a slightly different location. I'd have actually gotten 3.13 centimeters cubed, just so you know. And both answers are right. It's just for the different unit. Okay, we have a little bit more to go in this lesson. Switching gears slightly to mass. Mass versus weight. So mass is the amount of matter an object contains. Your weight actually depends upon the force of gravity. So perhaps you've been to a location before, like the Science Museum in Oklahoma City, where you can measure your weight on the moon compared to your weight on Earth. It's different because gravity is different on the moon than it is on Earth. So your weight is how much force gravity exerts on the object's mass. Mass is not affected by gravity. Right? The matter that's there is the matter that's there. I don't really weigh any less on Earth than I do on the moon, right? That my mass isn't any less on Earth than it is on the moon. But the force of gravity being less means that my weight, which affected by mass, is different. I mean, a weight affected by gravity is different. Our English units for weight are pounds and ounces. We also have the English ton. So you may have seen measurements of tons on bridges before, where it tells you how big like a truck can be going over a bridge. There's sometimes weight limits on older bridges, and it'll tell you it can only be a 4-ton truck or something like that. This is the English ton. Metric units for mass are based on the gram. Our mass, if we were looking at it in terms of our weight, right, like that sort of object, would be in kilograms, because the grams would be quite large, so it would be done in kilograms. A couple more conversions as it relates to this. There's 2 different charts here. The first one is the units for mass in a chart based on grams. Unfortunately, while over here it mentioned an English ton, there's also a metric ton. So that's fabulous, right? You got the same word and everything. A metric ton has the symbol that's a lowercase t. It's equivalent to 1 million grams or 1,000 kilograms. And as you're working your way down, the others we've already seen before. And then the other chart that shows up is just a couple lines, so it's not inside of a chart box. But it's a relationship between cubic units, right, like centimeters cubed, milliliters, and grams. That's the relationship between those 3 objects. Centimeters cubed, milliliter, and gram are all the same quantity. And then a decimeter cubed is the same as a liter, which is the same as a kilogram. Those are the conversions. All right, so let's take a look at some conversions. We'll see if we can get it finished today. I sure hope so. We're converting our 3,689 grams into metric tons. So if we set up our conversion fence, right, we have 3,689 grams. And we want the relationship of turning grams into tons. And that was along the top of my chart. it says that 1 ton is equal to 1 million grams. So 1 ton is 1 million grams. You're welcome to let your calculator do that division, 3689 divided by 1 million. Doing so, however, just moves the decimal point 6 to the left, okay? So you can also just move your decimal point 6 to the left. Either way, you end up with 0.03689, and it is metric tons. Number 8's kind of interesting just to make an awareness factor. It talks about the relationship between cubic objects and then capacity and mass, kind of like this chart right here. Cubic objects, capacity, and mass. And so it talks about 1 meter cubed. And 1 meter cubed in terms of decimeters is actually 1,000, right? Because it moves. Think again, you have King Henry died by drinking chocolate milk. And if you're moving from your base unit of meters into decimeters, you just move it 1 decimal place, right? So it becomes a 1 into a 10, but we do it 3 times because it's cubed. So this is 1,000 decimeters cubed. And over here it tells you what 1 decimeter cubed is. 1 decimeter cubed is 1 liter, it's 1 kilogram. So if you imagine taking this and making it 1,000, they would all be 1,000. Is everybody tracking with me on that? Whatever they are, they're equal. So over here I have 1,000 decimeters cubed, so therefore I have 1,000, liters and kilograms. 1,000 liters and 1,000 kilograms. So this question asks us for a capacity of 1 something. Well, 1,000 liters is what it's wanting in here, is the same as 1 kiloliter. Because again, put your liters right here, 1,000. And if you moved it 3 places over, you'd move the decimal point 3 to the left, and you get 1 kiloliter. Same thing for my was it kilograms or was it grams? Did I write it right? Yeah, 1,000 kilograms. So 1,000 kilograms would be what would go down here, but the relationship between 1,000 kilograms and its metric component over here along the top is 1 metric ton. So 1,000 kilograms would be 1 ton. I'll put the word metric in just to be clear because we have 2 types. 1 metric ton. All right, last example, and then we'll talk about what happens with your homework. Yes, ma'am?
How would we know that that's what it counts?
Because it used the number 1 here. I need something where it has a unit of 1 after it. I mean, 1's the number they gave me. I need to put the unit afterwards that matches it. And the one that it doesn't, when I have the number 1,000, I've got to change it into something that does work. That's a good question. An Olympic-sized pool in the shape of a right rectangular prism is 50 meters by 25 meters, and it's 2 meters deep. And we're wanting to know how much water does it hold. So the volume for a right rectangular prism is length times width times height. And they actually give us each one of those units, right? They give us the length, the width, and the depth or the height. So these are my 3 values that it gives me. And if I multiply them together, I get 2,500 cubic meters. The kicker is that it asks for the answer in terms of liters of water, not meters cubed. So I need to change my 25 cubic meters somehow into liters. I feel like we're going to fill it up with soda bottles or something like that. That's what it sounds like, right? Yeah. Okay, so we're going to set this up with a conversion. And you can do it with fences or with moving decimal places. So if you look at your cubic meters, I know I'm a tiny bit over. Just hold tight with me. We're almost done. If you look at your cubic meters, somewhere we had that. There it was. My cubic meters is 1,000 cubic decimeters. That's where I'm going to go first. My goodness, these slides are really far apart. So 1 meter cubed is 1,000 decimeters cubed. And then I need to turn my decimeters into liters, and there is a relationship right here that tells me 1 decimeter cubed is 1 liter, right? It's a 1-to-1 correspondence. So over here, my 1 decimeter cubed actually is 1 liter. So all I really need to do is to multiply my 2,500 by 1,000. And when I do that, I get 2,500,000. And then, of course, my units canceled along the way. Meters cubed canceled, decimeters cubed canceled, and I'm left with my liters. Okay, so here's the deal. We'll do the group work for this next time in class, so we're not going to turn it in. However, I will take questions at the beginning if you have them, so I'd encourage you to start the process because I can't take questions on Monday because you're taking a test. So I want to give you an opportunity to at least try some of the problems and ask some questions if you have some of them on Friday, but we won't turn it in on Friday. Does that make sense? Excellent. Yes, Emily?
Are we turning it in on Monday?
We'll turn it on Monday. So I'll change the due date inside of Canvas here in a moment so it'll say that it's due on Monday, but I would encourage you to at least start it between now and Friday so you can ask some questions if you have any, but we'll do group work for it in class Friday. Okay? All right. Have a great couple days, guys.